sharing your screen now. We now have Naveen Prabhakar from DIFR. Naveen is going to talk on a Hilbert space for the Chern-Simons matter theory. So Naveen, are you around?
Yes, Prasanta.
Good, it looks
Can you
good.
hear me?
Yeah, I can hear.
Can you also see my pointer?
Yes, it's perfect.
Okay.
So I will remind you after 9 minutes. Is that okay?
Sure. Yeah.
Yeah. Please go ahead.
Yeah. Just one small correction. I am now a postdoc at ICTS.
Okay.
But part of this work was done when I was at TIFR,
Yeah.
so I guess you're not completely wrong.
Okay.
Okay. Anyway, thank you, Prasanta. I would like to first thank the organizers for giving me this opportunity to speak here in this conference. It's good to be back among the community. So let me start. So I'll be speaking on a Hilbert space for
listen to this talk.
Chern-Simons matter theories, and it'll be a short summary of what Shira spoke yesterday. So it will be. Let me make it full screen. Okay. Yeah. So it'll be based on these two papers. One which came out last year with Shiraz Minwala and Amiya Mishra, and one which is due this month, which is called the Hilbert space of large Chern-Simons matter theories, with Shiraz Minwala, Amiya Mishra, and Tarun Sharma. So very briefly, the kind of theories we will be interested in 3 dimensions is these parity violating gauge theories called Chern-Simons theories, which are based on a gauge group and coupled to matter in the fundamental representation. So that's going to be the purview of my talk. So there's one thing to remember here, which is that this gauge coupling constant is forced to be an integer because of large gauge transformations, invariant set of large gauge transformations. And we also consider non-semi-simple gauge groups like UN, where the U1 and the SU part can have different levels. So I have chosen the gauge groups here appropriately to illustrate what is called Bose-Fermi duality, which I'll be coming to in a second. So why are Chern-Simons matter theories interesting? So these are exactly solvable in the 't Hooft-Largen limit when the matter is in vector-like representations, like the one here in the fundamental representation. We could have many flavors as long as the number of flavors does not come close to the number of colors here. So that will define a vector-like representation. And these Chern-Simons matter theories turn out to be holographic duals of many gravitational theories on ADS4. There is a rich literature behind this. And because of the underlying topological field theory, which is Chern-Simons theory, one would expect anionic excitations. And these theories typically exhibit anionic statistics, which will be one of the main points of this talk. And these theories also exhibit what is called Bose-Fermi duality, which is a duality which does not demand the existence of supersymmetry to be established. So for example, Chern-Simons theory coupled to bosons is dual to Chern-Simons theory coupled to fermions. And there is also a change in the rank and the level of the gauge group, which I have chosen here. So the rank and the level have to be flipped at the same time as the statistics of the matter particles here. And there's a small technical point, which is that an SUN gauge group is related to a UN type of gauge group on the other side. So very quickly, let me talk about the observable that I'll be interested in. I'll be looking at the partition function on S2 times S1. And we start by working in the large spatial volume regime. That's the volume of the S2 being large compared to other length scales in the theory. And the lightest mode in this theory, which is well known, the study of Yang-Mills or any gauge theory on S2 SD times S1, will be the gauge field holonomy around along S1, and the mode which is constant along the spatial manifold, which is S2 here. And using gauge invariance, we can always diagonalize this lightest mode to an n by n diagonal matrix. And this will be the field which we will express our expressions in terms of. Okay, so the next step is to integrate out all the matter fields and the non-holonomy fluctuations of the Chern-Simons gauge field to give an effective action for this holonomy U. And in the larger limit, one can see that this effective action scales as n, and hence we can compute this partition function z by saddle point approximation. So the saddle point approximation takes this form. So there is there is this observable U, which is, or rather the field U, which is this holonomy mode. And in the process of computing the saddle point, it turns out that it's convenient to introduce auxiliary C number variables in the large n limit, which I parameterize as phi aux. So the integrand, which we have to extremize, takes this extremely simple form, which is exponential of an interaction part, which I'll explain in terms of this example in a minute, which depends only on these auxiliary variables, times the usual Fock space trace of the matter particle that's coupled to the gauge field. But the trace is twisted by this holonomy element, which I denote as U hat, the operator which acts on states of this Fock space. For example, when we have Chern-Simons coupled fermions, the interaction effective action is given by this, which is just a function of these auxiliary variables, which I call as C tilde and curly C. And here MF is the mass parameter, the Lagrangian. And when we integrate out or extremize over the auxiliary variable C tilde F, that the on-shell value, that is the extremum value of that, turns out to be the thermal mass of this fermion. And this other auxiliary variable, we don't have a good enough physical interpretation as of now. And the final part, which is this trace over the Fock space, when we exponentiate it as a log of something, that becomes this. This also must be familiar. The only new element here is that this U twist appears as this n by n matrix U inside this log. And for bosons, we would have a 1 minus here. And there are other additional terms which depend on the chemical potential for bosons, which I will not have time to go into, but they're present. So this energy here, because we are in the large volume regime on S2, we can approximate that in the large n limit by a theory on R2. And the spectrum is just the spectrum on flat space, and that's given by square root of C tilde square plus K square. K is the spatial momentum. And on the extremum, C tilde just becomes the thermal mass of the fermion, and this will be the energy level with spatial momentum K. So once we have this split in terms of S interaction and this trace over the Fock space, we see that the dependence on the chemical potential appears only through this Fock space quantity. So obtaining the occupation number is very simple. We just differentiate with respect to mu. And the answer would be something like this. It's extremely simple. This trace is just the trace over n by n matrices. And this U is the extremum value of the holonomy mode. And for bosonic occupation numbers, like I said, there is a minus sign here, and we have this. So in the large n limit, the trace is replaced by an integral over the eigenvalue density function. And now the eigenvalues will be concentrated on arcs on the unit circle. And one should be careful as to how one does this contour integral in these cases, because sometimes there may be poles which may arise, for example, when this argument is less than 0, which happens when the energy is below the chemical potential, which in turn happens when this thermal mass is below the chemical potential. So one should be careful in such finite density cases. And one thing we can notice now is that because of the appearance of this holonomy mode here, the usual Bose-Einstein statistics or Fermi-Dirac statistics are modified in terms of these Chern-Simons couplings. And these gives rise to what we call as anionic statistics. So it lies somewhere between bosons, the occupation statistics for bosons and fermions. To illustrate this, for the sake of time, we look at this extremely simple limit, which is the large volume zero temperature limit of the above formulas. And in this case, the extremum U can be shown to assume this universal form, this n by n matrix with these diagonal elements. And plugging this back into this trace, we see these extremely simple numbers for these occupation numbers of the bosons for various states and for fermions. And for fermions, let's look at the fermions first because it's easier to relate to. For energies less than the chemical potential, we expect the state to be fully filled at zero temperature, subject to the Pauli exclusion principle, which says that there are n fermions, the number of colors here. And for energies above the chemical potential, we at zero temperature, we don't expect the states to be filled at all. And that gives the correct number 0 here. And this is some, in the regularization that we adopt, we get this intermediate value of half NF for energies right at the chemical potential. Now, what is surprising now is that after coupling these bosons to Chern-Simons gauge fields, the singularity in the Bose condensate, which arises basically because for energies below the chemical potential, the states have to be filled, but we can add any number of bosons in a particular energy state that is regulated to this number kb, which is just the Chern-Simons level of the Chern-Simons gauge field coupled to the bosons. And similar to the fermions, the energy levels above the chemical potential are not felt. So we see a Fermi surface kind of behavior in these bosons coupled to Chern-Simons gauge fields as well. So this is in line with the Bose-Fermi duality, because in the infrared, we expect a theory of bosons coupled to Chern-Simons gauge fields to be dual to another theory coupled to the theory of fermions coupled to Chern-Simons, and that theory exhibits a Fermi surface. So this kind of Fermi surface behavior is important. And under level rank duality, the level and the rank are interchanged between the bosonic and fermionic theories. So these two formulas are bang on for that. So
sorry,
in particular,
Naveen, this is just to remind that you already spent 9 minutes.
9 minutes, okay.
Yeah.
Thank you, Prashant. So this hints at an exclusion principle for bosons, and let's flesh it out. So first of all, we took a lot of limits in coming to this conclusion, the large volume, zero temperature, large N limit. But if it's an exclusion principle, we expect it to be more fundamental. And it turns out that if we study the partition function at large N more carefully, we can uncover this more fundamental aspect of the exclusion principle. So suppose we focus on the U-dependent part, this Fock space trace. We can expand using usual Fock space manipulations to write it as this. So there is a piece for the particles and a piece for the antiparticles, and this chi is just the character for the symmetric N box representation, where N is the number of bosons in a particular energy state EA, evaluated on this matrix U. And we are integrating over all matrices. So in the large N limit, we have to extremize this, but I'm just retaining the integral because we'll make contact with something deeper in a minute. Some more manipulation just gives this following formula, where we have pushed this integral over U and isolated the parts which are dependent just on U. And now, if we look at this, this is just an observable in the pure Chern-Simons theory with an infinite number of Wilson line insertions, which is what I've written here. So there's this usual Chern-Simons action with the Wilson lines corresponding to the particles and the antiparticles. And the finite N version of this is well known. It's just the Veblen formula for the number of singlets in the fusion of the representations SNA for all A and SMA for all A in the dual chiral Weissenberg model. And this is the same as the dimension of space of chiral conformal blocks with these representations. And long ago, Gettner and Witten showed that conformal blocks in WGW models with some integrable representations and one or more non-integrable representations vanish due to a null vector in the module corresponding to the integrable representations. Incidentally, the condition for integrability for a representation of SU and K turns out to be that the number of boxes in the symmetric representation should be less than or equal to K. So this says that the dimension of conformal blocks corresponding to representations which have more than K boxes will be 0. And in particular, that tells us that this integral is 0 if one of these insertions has more than K boxes. So this allows us to restrict the sum, which was from 0 to infinity earlier, to just this level KB. And this implies the bosonic exclusion principle. And since this Chern-Simons chiral Weissenberg duality is rigorously established, this is also a very fundamental fact that's present in the Chern-Simons theory coupled to bosons. So in the last 1 minute remaining, let me focus a little bit on some technical aspects of this Chern-Simons chiral Weissenberg duality. So suppose we consider this observable in pure Chern-Simons theory based on the SU gauge group at level K, which has these N Wilson lines inserted with representations R1 up to Rn. So this is basically the dimension of the Hilbert space of states in the pure Chern-Simons theory with sources in these representations. One can evaluate this path integral using standard path integral techniques, which Blau and Thompson did about 20 years back. One could also do this in a slightly roundabout fashion by embedding this back in a n equal to 2 Chern-Simons theory on S2 times S1, and again lift these ordinary Wilson lines to supersymmetric Wilson line insertions and compute the superconformal index. And because the fermions in this theory are quadratic and we can integrate them out, this will just reduce to an observable in the pure non-supersymmetric Chern-Simons theory. This is another independent way of obtaining the same quantity. There is a third way which appeals to this Chern-Simons Weissenberg correspondence. So before that, let me just briefly describe Blau and Thompson's result. So this turns out that once you do this path integral carefully, this integral over gauge fields reduces to a finite sum over some eigenvalue configurations, that is the holonomy mode, some discrete set of holonomy modes. And so here, this is the usual van der Monde determinant that we encounter in gauge theories. And the Wilson lines just reduced to characters evaluated on the matrix U, like we discussed earlier. But the matrices U correspond to special eigenvalue configurations, which satisfies these equations here. So the first condition just says that it's an SUN matrix. And this van der Monde factor here does not allow coincident eigenvalues. But thirdly, the third condition is the new one, which is from the Chern-Simons Lagrangian, which is that ratios of these eigenvalues have to be kappa threads of unity. That's another way to say this, express this condition. So there is another, like I was saying, there is another way to obtain the same dimension of Hilbert space through this correspondence, which is due to Verlinde. So that expresses this as a sum over integrable representations of this affine Lie algebra, SUNK hat, of this particular product of product and ratios of Verlinde S matrices. And this formula holds only when R1 or Rn are integrable representations of this affine Lie algebra. Now, the two descriptions, that is one from the Chern-Simons path integral and the one from the Benjamin-Witten model, are related because of a magic formula that relates the S matrix, the Verlinde S matrix, to classical characters. And that's basically this. So this is one of the factors in this expression here. So suppose I have something like this, that is equal to the character of the representation R prime, the ordinary representation R prime of the ordinary SUN Lie algebra, evaluated on this particular matrix U, where this eigenvalue configuration is described as follows. So it's related to this representation R, that is on the left-hand side. So suppose the row lengths of the Young diagram of this representation R are given by Li, with, of course, the last row being 0 because it's an SUN representation. And suppose this Ni is the sum of Li plus capital N minus I. Then these eigenvalues are given by this particular formula. So it's very easy to see that these eigenvalues satisfy these constraints that I wrote down. So they are, in particular, they appear in the set of configurations that we sum over. We show that the converse is also true. That is, any solution to these equations here can be expressed as W of R, where R corresponds to an integrable representation of SUN hat K. And further, the explicit formula for the S matrix for SUNK hat gives rise to this equality here, which appears here. So that basically reduces to the van der Monde determinant in the three-dimensional path integral. So this finally establishes the equivalence of the two-dimensional Verlinde formula with the three-dimensional Chern-Simons path integral. And similar relations can be established between UN K, K prime WCW theories and the corresponding Chern-Simons theories. So this is one part of the paper that's going to come up soon. So finally, I would just like to highlight some observations. So here in this short summary, I outlined this relation between eigenvalue configurations in the three-dimensional path integral and integrable representations of the affine Kac-Moody algebra. So this kind of is in line with this abstract harmonic analysis, which one can do for classical groups, where conjugacy classes in G, which are typically parameterized by diagonal matrices with non-coincident elements, are in one-to-one correspondence with the irreducible representations of the classical group. Here we have something that's similar to the story for the finite group, which is we have a finite set of irreducible representations, which are the integrable representations of the affine Kac-Moody algebra, and some distinguished conjugacy classes given by these matrices here, which satisfy these equations for the case of SUN. So what is the object that this corresponds to in the case of the classical group? Yeah,
please try.
This is my last slide. So let me just summarize. Yes, thanks, Prashant. So the other question is that, so what is this object? That's one thing that we are planning to explore next. And the other point is about non-integrable representations. The Verlinde formula gives the correct answer only for integrable representations, but the Chern-Simons path integral naively does not seem to care because we can take any representation we want along the Wilson line. But what it turns out that when we look at the characters evaluated on the special eigenvalue configurations, the character of a non-integrable representation evaluated on any of these eigenvalue configurations can be related to that of an integrable representation up to a sign. So there are identities among Wilson lines in the Chern-Simons theory, which basically tell us that the independent Wilson lines in the space of Wilson lines correspond to those of integrable representations. But it would be nice to see actually the fact by Gepner and Witten, which says that the conformal block with one at least one non-integrable insertion is 0 in the Chern-Simons path integral. So I'll conclude here. Thank you.
Okay, thanks, Naveen. So we have one quick question from Somadat.
Yeah, so because of the presence of the U in the partition function, the statistics has become the anion statistics instead of bosons and fermions, right?
Yeah.
So
yes.
Why do you continue to speak in terms of bosons and fermions then?
Well, in the ultraviolet, the fields that we use are still bosons and fermions. It's just that in the infrared, the effective description is in terms of anions. We do not have a fundamental field theory description of these anions. And we can always...
Even in the ultraviolet...
Okay, quick. Somadat, can we go to the next question? Maybe you can ask in the discussion session.
Sure.
Quickly.
Hi, Naveen. Thanks for the talk.
Hi.
So at some point, we also calculated this for starting from Wisdom to Witten side. And there we have this integrable representation, all these things boils down there. But probably I missed in your talk. So are you guys, what is the manifold that you are considering on your Chern-Simons theory?
S2 times S1.
S2 times. So do you have any comment on S3? Because we have some calculations where with this integrable representations were giving us some phases, some non-trivial phases because of this integrability, exactly of this integrability condition, because Chern-Simons part does not care about non-integrable representations, you see.
I see, so I don't have any intelligent comments except to say that perhaps one can use our answers on S2 times S1 and then do surgery to get some answers on S3. But I mean, I'm not sure how hard or easy that would be.
Right. I mean, for S3, it would be interesting.
Sorry, Arjun, maybe,
Sure, thanks.
Can I continue in the discussion session? Yeah, okay.
Sure,
as we're running out of time. Okay, Naveen, thanks a lot for the nice talk. Please stop sharing.
Yeah.
So now